Hi and welcome to Shows's classes. Today we are going to be dealing with some very important questions that usually students have problems with. You can call or WhatsApp at the number given on the screen for doubts or full videos on our courses. Let's see a new sum. Now we have a very big question. What is known as the characteristic line of modern investment analysis is the simple regression line obtained from the following model. RIT equals to alpha I plus beta I RMT plus UT. Here RIT equals to the rate of return on the ith security in time t. RMG is the rate of return on the market portfolio in time t, and UT is the stochastic disturbance term. In this model, PI is known as a beta coefficient of the ith security, a measure of market risk of a security. On basis of a 240 monthly rates of return for the period 1956 and 1976, Fogler and Ganpati obtained the following characteristic line for IBM stock in relation to the market portfolio index developed at the University of Chicago. RIT equals to 0.7264 plus 1.0598 RMG. SE equals to 0.3001 into 0.0728, R square equals to 0.4710, DF equals to 238, and F 1.238 equals to 211.896, and hence we are given most of the values. We need to figure out a security whose beta coefficient is greater than 1 is said to be a volatile or aggressive security. And now we need to figure out, was IBM a volatile security in the time period under study? Let's see how to do this. Now we use t-test to our hypothesis that the true slope coefficient is 1. That is obtained t equals to beta 2 cap minus 1 by standard error beta 2 hat. This equals to 1.0598 minus 1 by 0.0728 equals to 0.821. For 238 degrees of freedom, this t value is not significant even at alpha equals to 10%. The conclusion is that over the sample period that has been under the study for IBM was not a volatile security. Let's see another important question. To read the question, we are given certain values of ESS, RSS, RS square, YI, SE, and their meanings of each terms are also given. Now the first one asks, how do we interpret this regression? Well, there is a positive association in the LFPR in 1972 and 1968, which is not surprising in view of the fact since World War II there has been a steady increase in the LFPR of women. Now let's see what number B has to offer. We need to test the hypothesis H0 beta 2 equals to 1 against the alternative hypothesis H1 is beta 2 greater than 1. Which test do you use and why? What are the underlying assumptions of the test you use? Let's see how to do this. We use the t-test just like our previous question. T equals to 0.6560 minus 1 by 0.1961, which equals to minus 1.7542. Mind you, this is a one-tailed test. Now for 17 degrees of freedom, the one-tailed t-value at alpha equals to 5% is 1.740. Since the estimated t-value is significant at this level of significance, we can reject the hypothesis that the true slope coefficient is 1 or greater. Number C says, suppose that the LFPR in 1968 was 0.58 or 58%. On the basis of this regression, we have to figure out what is the mean LFPR in 1972. We have to establish this at a 95% confidence interval for the mean prediction. Let me clear the screen so that you can see the question. The mean LFPR is 0.2033 plus 0.6560 into 0.58, which closely comes to 0.5838. Now to establish a 95% confidence interval for this focus value, we use the formula 0.5838 plus minus 2.11. This is the standard error of the mean focus value, where 2.11 is the 5% critical t value for 17 degrees of freedom. To get the standard error of the focus value, we use the formula. Please note that since the authors do not give the mean value of the LFPR of women in 1968, we cannot compute the standard error. And lastly, let's see what number D has to say. How would you test the hypothesis that the error term in the population regression is normally distributed? We need to show the necessary calculations. Without the actual data, we will not be able to answer this question because we need the values of the residuals to plot and obtain the normal probability plot or to compute the value of the Jark-Bera test. With this, we come to an end of another video. Please like, subscribe and click on the notification button and contact us for any doubts or full videos on our courses.